Hi, I'm Jacob Scott. I'm going to talk to you about some things that you need to consider when choosing your microcontroller to interface to your analog sensor. Obviously, the most important consideration is going to be the analog to digital converter in that microcontroller, and the most important parameter of that analog to digital converter, or ADC, is going to be the resolution. Resolution is the number of counts that you have from 0 voltage to the reference voltage or full scale of your analog to digital converter. You might remember from class the PIC processor that we used in the lab had a 10-bit A to D converter, so it had a maximum count of 2 to the 10 or 1024, so we could get a count of 0 to 1024 from 0 to our reference voltage, which was usually our supply voltage. Another important thing to consider is clock speed and your corresponding sample rate. You're obviously going to have a minimum sample rate that you need to sample your sensor at to keep the system running right, but you want your clock speed to be sufficient such that you can not only sample at that rate, but also perform all the other tasks that you need to perform when running the program. And then, of course, goes hand in hand with sample rate is your conversion time. You can't just take an ADC sample and have it ready immediately. You'll remember that you actually have to request the conversion, the ADC performs the conversion, and then you actually read it into your program once it's ready. An important thing to talk about when talking about conversion time is step recovery. Conversion time isn't always the same depending on the type of analog to digital converter you're using. This graph over here actually shows what I mean by a step. Here we have the red line, which is actually a ramp signal, which is being converted digitally. And at the top of the ramp, where it goes back down to the lowest level, the last sample is going to be significantly different than the current sample. Some analog to digital converters actually have a significantly greater conversion time for a step like that. So you need to consider when you're actually making your design whether or not you're going to have steps like that in your input signal regularly, and whether or not you need to choose an analog to digital converter based on that consideration. Tom talked a little bit, and Case talked a little bit about filtering for noise immunity. Obviously, you can implement some sort of circuitry externally to limit your signal, such as a bandpass filter or a low-pass filter, but what if you want to actually see a quick change in the signal, but not always, like in our case, where we actually may have slight, very quick spikes in the gastrointestinal pressure, and we may not want to react to those all the time. You know, like if a spike that's high enough will actually cause the test to stop, but what if that spike only occurs for, 10 milliseconds, either due to noise or due to some other reason? That's where software filtering comes in, where you either have a running average, or you have some sort of hysteresis where you don't always react to that. You only react to it when you need to, and that's a situation where you're going to want to use software filtering over hardware filtering, because hardware filtering would prevent you from actually seeing that in the first place. One other interesting thing about analog to digital converters is that they're man-made, and therefore they're not perfect. They will drift. Now, as technology has gotten better over the years, the drift is not as great in most analog to digital converters. However, you will see some drift over time in your analog to digital converter. So how do you compensate for that? It's actually really simple. A lot of devices have a externally calibrated voltage where you actually hook an instrument up to your device, whether this instrument either gives your device a set voltage or you calibrate the set voltage inside your device that's set with an op amp or whatever. And then in your software, you have a calibration routine that corresponds, that actually correlates that calibrated voltage to a count in your software. So you expect a certain count for a certain voltage. If you don't see that count, you can actually compensate in your software for that, which allows you to essentially eliminate the drift. Now I'd like to talk about our pressure sensor that we actually chose for our project. It's made by Measurement Specialties Incorporated. It's a piezo-resistive sensor in a Wheatstone bridge configuration. That diagram down there is actually a diagram of our sensor, which I'll talk about in a minute. This is actually an amplified sensor, so we don't actually have to worry about a whole lot of external circuitry, which saves us time and money, and basically allows us to connect the sensor directly to our microcontroller. This device is actually fully temperature compensated. We have a pretty rough environment in the lab, and so we wanted a sensor that actually had a decent performance over temperature, and this sensor does. This sensor uses current excitation, and as you can can see there, we have our current source going into our Wheatstone bridge configuration, and then the amplifier at the front end that I talked about. This sensor has a really fast response. It can go from 10% of its output to 90% of its output or maximum output in less than 10 milliseconds. So this will give us the performance we need to be able to react to those quick changes that I talked about in the gas to internal track. It has good noise immunity. One of the reasons for that is the current excitation. It's a very desirable excitation method in industrial environments where you're going to have a lot of electrical noise. And another nice feature about the sensor is the interchangeability. There's less than a 1% variance between parts, even between batches of parts. So this is something where if the sensor failed or if we were mass producing these, we could actually, put many sensors from many different batches into the devices and have very little variance between them. So, in summary, we covered passive sensors, active sensors. We covered choosing a microcontroller to interface to those sensors. We talked a little bit about the interfaces between the sensor and the microcontroller, and then we also talked about things that you can consider inside the microcontroller. Hopefully, with all this information, you can design a system with the end result of a working system. Any questions?
Any questions from the class? Come on, somebody's got to help me here. Okay, well, I've got one. Jacob, you can take this one on. So if you have 10 bits, how many quantization levels?
2 to the 10.
10, 24, right?
Yeah.
So if you start at 0, what's your maximum?
1023. Yep.
Okay, good job. I bet you guys were well organized and you look good.